All right, good afternoon, everyone. Welcome to Physics 304, Introduction to Quantum Mechanics. I recognize most faces, but in case there's anyone unfamiliar with me, my name is Jake Grabowski. My office, sorry, we're gonna get a little bit of an echo here, I think. Probably if you're up front, you can hear it. If anybody has like a old style headphone jack, I could make this little echo go away. But if not, then I'll fix it for next time. So my office is on the second floor of the science building at Science 266. And if you need to get in touch with me for any reason, you can email me at jake.pawlowski@ubc.ca. There is a course website, so here's the URL. You don't have to memorize it. The easiest way to get there is just to do a Google search for my name. The first result will take you to a page that has this link. Alternatively, you could just log into Canvas, go to the Phys 304 Canvas page, and the link to this website will be there. So let's do that. All right, so Phys 304 is here. All right, so there's not much on this web page right now, but what we'll do is I'll show you what it's going to have. I will be streaming these lectures over Zoom. I will get rid of the echo for next time. But as the recordings come in, I will post links to YouTube videos of the recorded lectures here, as well as anything I write on the tablet, I will convert to a PDF and then post that PDF of the notes right here as well. So you'll get recordings and notes for every class that we do, assuming I don't screw up the technology here. Okay, then the only other thing on the website are a syllabus and it talks about a Piazza page and the midterm, and so that's what we'll discuss here. So I do have a Piazza page. You can enroll if you want. What I do with Piazza is inevitably people ask me constantly to advertise A, B, C, and D to the class. And they want me to advertise things that really aren't connected directly to this class. And so rather than burn class time on those things, what I do is I post those to Piazza. Sometimes they're interesting, sometimes they're not. So some of the interesting things that might come up is, oh, like there's some conference for undergraduate physics students, or there's like a summer research opportunity, something like that. All of that stuff will go on to the Piazza page as an announcement. And I'm not going to specifically mention it in the class. So if you want to get those kinds of notifications, enroll in the Piazza page and you will get those. What I won't do on Piazza is I won't put stuff that's specific to this class. So assignments and dates and stuff like that that are specific to Physics 304 will go on the course website. So if you don't want Piazza notifications, you don't need to enroll. It won't affect your progress through the class at all. There is going to be a midterm, and it's already scheduled. It's October 20th. That's approximately halfway through the term. Okay, it'll be a regular in-class written midterm. The only other thing that's on here besides the syllabus is a recommendation to start reading the textbook. The textbook is this one. It's Introduction to Quantum Mechanics by Griffiths. Griffiths and Schrodinger. So it's quite a good book. You know, when I was a student, I didn't always read every page of every textbook, although I did read most of the stuff. This is one that is really quite readable. And so I have never taught the course before. I'm looking forward to teaching it. I expect to learn a lot. I'm going to follow the book closely. And so if you're not reading along in the book, you're not fully participating and holding your end of the bargain in this class. That's my opinion, okay? So when I say I recommend that you read chapter 1 of Griffiths, that's a very strong recommendation. And so to be fully engaged in the course, you will have to keep up with the readings. And in fact, what you should be trying to do is to read ahead of the lecture so that you know what's coming. You're not coming into the class completely blind with no idea of what we're going to talk about. So my expectation is for a regular class, you've already read the material in the textbook, and what I'm going to try to do is to give some details, do some practice examples, things like that. Okay. So the only other thing that's on here is a link to Canvas. In Canvas, what I'll do is I'll post your grades throughout the term. So as assignments get marked and things, that's where your grades will go. That's about all I'll use Canvas for. Okay. All right. Any questions about anything so far? Yeah.
Will this work for that go?
Oh, yeah, thanks. That will work. Ooh, maybe what I'll have to do is pop this thing out of here for a second. All right, that's better. Thank you very much. Yes.
Do you know if for the textbook, if we had found access to an earlier edition, what would that?
Oh yeah, that will be fine. So I've got the 3rd edition. I think that's the most recent one, but if you get 2nd or 3rd for cheap or whatever, that's going to be fine. It'll just mean maybe that the problem numbers at the end of the chapter might have a different number, but I think that will be totally okay. All right, so let's open the syllabus and see what's in there. I'm not going to spend a lot of time reading it to you. You can go through the stuff on your own. So textbook, we already talked about. Earlier editions are okay. So yeah, it actually says that in there. Piazza, we talked about. Office hours, I do have some office hours, and there they are. So this is just online. Anybody can look at it at any time. My office hours are today, sort of just before lunch, and Monday right around lunchtime. I don't know everyone's schedule. It's may well be that you have conflicts with both those times. If that's the case, you can just show up to my office. If I'm in there, I'll likely make time for you unless I'm on my way out to another class or something like that. Failing that, you can just send me an email to book a time. If you do that, I recommend that you just have a look at the schedule first, find the gaps, and then suggest we meet at one of those times when I'm not in some other class. Okay. Anything else worth talking about in here? Evaluation. The evaluation is just really straightforward. There'll be assignments, midterm, and a final exam. Okay, and so I've got here like a tentative schedule. Again, I haven't taught the course before, so there'll likely be some changes to this. I talked to the two people that have taught this course most recently, and what they recommended is that we focus on trying to get through chapters 1 to 4. And so that's what I'll do. If we have time at the end, like we finish this material up, then we'll select some topics from some later chapters without covering the material that you'll see in 402, which is the follow-on course to this one. Okay, other than that, there's just official policies that they make us put in the syllabus. You can read those or not. It's up to you. All right, any questions about anything at all? No. Okay, good. So enough of all that nonsense. Let's get started with the interesting stuff. So what we're going to do is we're going to start in chapter 1. So let's go Griffiths. Chapter 1. And the chapter is called the wave function. And the first section is Schrodinger's equation. So I assume that you've seen some introduction to the Schrodinger equation in Physics 200, but even if you have, we're going to do a little bit of a review of that because it's central to essentially almost everything that we'll talk about in the course. And so let's just start by thinking about classical mechanics, a subject that we know and have studied in several different courses. So in classical mechanics, one approach to solving a problem is we solve the equation of motion. To determine an object's dynamics. And so by dynamics, what I mean is how does an object's position, velocity, and acceleration evolve with time? Once we know these quantities, we can solve for a whole bunch of other dynamical variables. So once these are known, we can calculate all other dynamical variables, such as the momentum, which is just mass times velocity. We could take a derivative of the momentum and we could get the force. We could calculate kinetic energy, 1/2 mv squared, and so on. So position, velocity, and acceleration unlock the key for all of the kind of time-dependent quantities that we might be interested in about a particle or a system in classical mechanics. Of course, we need a mechanism to solve for x, v, and a. And what we're going to use is Newton's second law. So Newton's second law gives us the equation of motion. Okay, and Newton's second law is just F equals ma, is how you usually represent it. However, we could also write this in a more interesting or more revealing way, and we could say that, well, this expression is really a differential equation in both position and time, since in one dimension, we could write that a, the acceleration, is two derivatives of the position with respect to time, and the force, for at least a conservative force, we could write it as a derivative of the potential. We don't usually write it that way in like a first year course because that's a little more intimidating than just a simple F equals ma, but an equivalent expression is that m d2x dt2 is equal to minus dv dx. And so here is a differential equation in time and position that if we solve it for some given v of x, will give us the position, velocity, and acceleration of our particle, from which we calculate momentum, kinetic energy, force, and all that stuff. Okay, one thing I want to emphasize here is that Newton's law is not derived from any kind of simpler or more basic principles. It's an axiom of classical mechanics. So we note that Newton's second law is not derived from something more fundamental, rather it is an axiom of classical mechanics. And Newton came up with this axiom based on observations of how objects interact with one another and with, various forces. Let's classical. Okay, I won't write it down, but I'll qualify that statement slightly. Next term, many of you will probably be taking Physics 328, which is our advanced mechanics course. In a course like that, you'll learn about Lagrangian mechanics. So it's another nice formalism of mechanics. So in that case, you can start with Lagrangian mechanics and derive Newton's second law. However, it's not like you're getting something for nothing. You're just trading in one axiom for Newton's second law for some other axioms that lead to the Lagrangian. So you can pick and choose which axioms you want to work with, but at some point, you're always starting with some assumptions. All right, so that's kind of like a little recap of some of the approaches to classical mechanics. In quantum mechanics, we likewise have an axiom. We likewise have a foundational axiom. It is called Schrodinger's equation. Schrodinger's equation. And it takes the following form. Like Newton's second law, it's going to be a differential equation in time and position, but it'll look slightly different. I'll just write it down. It'll be IH bar, and then one time derivative of this function psi. So this is psi. It's actually capital psi, so maybe I should psi. So it's a Greek letter. Okay, so that's the left-hand side of Schrodinger's equation. And then on the right-hand side, we have minus h bar squared over 2m. And now we have two derivatives of this function psi with respect to x. And then we have a potential energy times psi function again. So this is potential energy. All right, so I'm going to call this equation 1, and it's Schrodinger's equation. All right. What I will try to do, I think we'll do it this class, is we will try to come up with like a justification for why this works, at least in a special case. But we can't derive it and say that this always works. It's an axiom. It's something that we're going to suppose works, and we're just going to work through all of the mechanics of applying it and see that it does give us the correct solutions to our systems that we're going to be interested in. So like the equation of motion, it is a differential equation in x and t. We will see shortly that Schrodinger's equation tells us, or let's say is related to the energy of our system. Okay, what we're going to find is that here's the potential energy. This is going to give us something like the kinetic energy, and then that will be equal to total energy. And so we'll see how that comes out over the next couple of classes, I expect. All right, so what of this function psi of xt? So that's going to be our wave function. So psi of xt is called the wave function. And so for now, we can think of it as representing, whoops, a single microscopic particle like an electron. And so solving Schrodinger's equation, how this wave function varies with position and evolves with time. Okay, so before going any further with these kind of abstract terms, what I'd like to do is I'd like to show you one sort of quasi justification for why Schrodinger's equation works. Okay, so I can't derive Schrodinger's equation. So why don't I say I can't derive equation 1, but we can try to motivate it. Motivate it. And so in order to motivate it, what we're going to do is we're going to appeal to something that you would have talked about in Physics 200, where de Broglie postulated that all particles, like matter, particles with mass, also have like a wave kind of character. And specifically, the momentum of the particle is related to its wavelength. So let's consider matter waves as proposed by de Broglie. And so what he said is a particle's momentum is given by P equals h bar k, where k is equal to 2 pi over lambda. Okay, so k is often called wave number. It's essentially inverse wavelength. Okay, just like omega is 2 pi times frequency, k is 1 over lambda with a factor of 2 pi thrown in there. Okay, so its momentum is h bar k, and its energy is given by E equals h bar omega, where omega is 2 pi times f. All right, so what I want to do is I want to try to represent such a particle in this kind of wave picture. So if we represent our particle in the wave picture, as a plane wave. So I'm just using plane waves because plane waves are functions that have a definite frequency, so some definite energy for our particle, and a definite wavelength, so some definite momentum. Okay, so we would say psi of xt. So the form of a plane wave is as follows. This is also sometimes called a traveling wave. And so here, its spatial component varies with this factor k, this 2 pi over lambda, and the time evolution is given by omega times t. Okay, so if we do that, then we can say, well, Schrodinger's equation is going to involve a time derivative of this wave function. And if I take this time derivative, I'm going to bring down a factor of minus I times omega. So this would be minus I omega. And then because the plane wave is just an exponential, we take a derivative, we get that exponential back again. So we just get this wave function back. And then we have to do the same thing for the spatial derivatives, but this time we have to take 2 of those derivatives. When I take the first derivative, I get a factor of ik coming down. So we'll get ik, then times the wave function. But then I have to take the derivative again, which brings down another factor of ik. So we get ik squared times that wave function. And so let's just note that I is equal to the square root of -1. So here I have I squared. That's just going to become a minus sign. And so we get minus k squared times the wave function. So our assumed form for this wave function with some fixed energy and momentum leads to these results for the derivatives, and we could just stick these into our Schrodinger equation and see what happens. So subbing these results into Schrodinger's equation, equation 1 gives. Okay, well let's go look back at what we had. So the time derivative, we have to multiply by IH bar, and the spatial derivatives is multiplied by minus H bar squared over 2m. Okay, so let's see if we can do that. So we have IH bar, and then we multiply by the time derivative, minus I omega, and then we get the wave function. Okay. Equals, we have minus H bar squared over 2m, and then we multiply by the spatial derivatives. And then nothing happens to the potential term. That just comes along. All right. But let's just examine this term by term and see what happens. I have minus I times I. So that's minus I squared, or it's minus 1. So it's plus 1. And then we have H bar omega. So this is H bar omega. But we just said in our kind of wave picture of particles that E is equal to H bar omega. It's the particle's energy. And so this is just equal to E. And then if we look at this next term, let's see, the minus signs cancel, and we get H bar K. I'm going to write it in this way. I'm going to write H bar K all squared over 2m. But we said H bar K was our particle's momentum. And so this is P squared over 2m. But momentum squared divided by 2m is just the kinetic energy. Whoops, sorry, this is K for kinetic energy. You could also put this as m times v, so it's m squared v squared. M squared divided by m is m, so we get 1/2 mv squared kinetic energy. All right. So if we bring all this together, what we're left with is E times this wave function is equal to K times the wave function plus V times the wave function. And so this is total energy is kinetic plus potential. And so this is an expression for E is equal to K plus V. And so that's a motivation for how Schrodinger's equation is telling us about the energy of whatever system, in this case, free particle, what we're thinking about. So for a particle with well-defined E and, well, let's say omega and lambda, Schrodinger's equation is equivalent to a statement about energy conservation. Okay, now all of this was done for a special case. It's not a general derivation that always works. So the leap that we're going to make, the leap that elevates Schrodinger's equation to an axiom, axiom of quantum mechanics is that we generalize and presume that it works for all types of systems. That it applies to all wave functions. Not just for particles with psi of the form e to the I kx minus omega t. Okay, and the further justification is that people have studied the Schrodinger equation for a long time with a variety of systems, both theoretically and experimentally, and they found that it gives very, very precise, accurate predictions of quantum mechanical behavior. All right, so what we're used to in classical mechanics is this ability to say, all right, given a set of initial conditions and knowing the forces between particles in a system, we can, in principle, no matter how complex the system is, always calculate the exact trajectories and time evolution of every particle in the system without any doubt. That's not going to be the case in quantum mechanics. In quantum mechanics, we're going to have to think in terms of probabilities, statistical probabilities of where we are most likely to find particles. And so it's a new kind of way of thinking. And so I want to try to emphasize some of that. And so this is going to be the statistical interpretation of quantum mechanics. So for those of you that took Physics 232 last year, we did a bunch of statistics. We talked about binomial distribution, Poisson distribution, Gaussian distribution. We talked about how to calculate expectation values. All of that stuff is going to be a major factor in this course. So if you're really on top of everything we did in 232, the statistics part of it, then that's going to save you a lot of trouble in this course. All right. So in classical mechanics, we solve for x of t, which represents a particle's position as a function of time. In quantum mechanics, we solve for the wave function, which represents a particle's so-called state. So we'll worry a little more about what state means later, but it just means, what energy does it have, what's its momentum, things like that. So what we're going to do is we're going to make some comments about Born's statistical interpretation of quantum mechanics. So Born provided a statistical interpretation of the wave function. And so what he said is, if you take the wave function, which is in general complex valued, in fact, we saw that already when we assumed this for our particle with a definite wavelength, there's the complex I in that wave function already. And in fact, if you just go back to Schrodinger's equation, I is in Schrodinger's equation itself. So these functions, these wave functions, are complex functions. Any real physical variable that you want to measure has to be a real quantity. So what we measure is not directly related to the bare wave function itself. It's related to the square of the absolute square of the wave function. So what Born presented or supposed is that if we took the square of a wave function and multiplied it by some small interval in space, dx, what that tells us is, well, okay, let me just write out what this actually means. So the absolute square of the wave function means that we take the wave function and multiply it by its complex conjugate. Okay, and so this is the complex conjugate of phi of xt. And so what Born said is this gives us the probability of finding our particle at some position between x and x plus dx. So this is the probability of finding a particle between x and x plus dx. And so let me try to draw this as a picture. So I'm going to draw some kind of coordinate system here. So this is x. And along the vertical axis, I'll put the absolute square of the wave function. And so that could look like anything. So for some fixed time, we might have, it would have to be positive. That's the only real restriction. And so I can make it arbitrarily complex or complicated. And so maybe it looks something like this. And then what we're going to do is we're going to say, well, okay, here is some position x. And here is some position x plus dx. And so this width here is dx. Now, we can approximate for, like I've drawn my dx to be pretty big. So the top of this is not flat. But if you shrink dx down and make it infinitesimal, very narrow, then this has an approximately constant height. And what we have is some rectangle with area of width dx and height given by psi squared. And so psi squared dx is estimating the area of this rectangle. So this area, the area is psi squared dx. And so what Born is proposing is that that gives us the probability of finding our particle between these two positions. All right. So in general, the probability of finding the particle between, say, A and B is given by, well, what I would do is I would find A somewhere along this x-axis, and then I would find B at another point along this x-axis, and I could divide that function into a bunch of thin rectangles and I add up all the areas of those thin rectangles between A and B, and that total area tells me the probability of finding the particle between A and B. But that process of adding a bunch of small areas together is just like integrating that function from A to B. So the probability that our particle exists between A and B is the integral of AB times the absolute square of the wave function, and then we integrate with respect to dx. Okay, so what's the units of a probability? Well, probability is just some number between 0 and 1, let's say. And so it's unitless. What about this dx? What's the units of dx? Some interval in position, some kind of length, right? So if I want to get a dimensionless quantity of some function that I integrate with respect to x, this has units of length. So this has to have units of 1 over length in order to get a dimensionless probability. So this phi of xt squared is a probability density in the exact same sense that if you were working with some Gaussian distribution, you would say the Gaussian function is a probability density. And so it's the exact same type of language that we're using. So the units of psi squared have to be 1 over length, since psi squared times dx is dimensionless. And so that means the units of psi right? If I don't square it and I just have the bare wave function, well, the squared version has units of length. And so the bare version has units of 1 over the square root of length. So typically, not typically, always, a one-dimensional wave function has units of 1 over the square root of meters. All right. So what would happen if I made A and B go to minus infinity and plus infinity? What would the probability be of finding my particle between those limits? Yeah, 1. Okay, so it must be the case that if I take this and I set my integration limits to minus infinity to plus infinity, then my particle exists somewhere in that space. And so there's another restriction on the wave function. So note also that if we want phi squared to represent a probability density, then we require, let's see, the integral from minus infinity to plus infinity of psi squared dx must be equal to 1. And so this restriction or this requirement has a name, and it's called the normalization condition. So when people talk about a normalized wave function, all they mean is that if I plot this wave function over all space, the area under the curve has to be equal to 1. Okay, so this is the normalization condition. The probability of finding our particle between minus infinity and plus infinity is 1. That actually leads to, in general, another restriction on our wave functions. And that is, if I expect this integral to be finite and equal to 1 when I integrate overall space, it must be that the wave function must vanish. It must approach 0 when x goes to plus infinity and minus infinity, right? I must have to cut off that area in order to get a finite area over an infinite interval. Okay, so normalization also requires that phi xt go to 0 as x goes to plus minus infinity in order to preserve a finite value for this integral. Okay. So I want to, okay, so first of all, how much of this is familiar from 200? Is this all kind of covered in physics 200? Okay, good. So I mean, that's a lot of the abstraction for quantum mechanics, is thinking in this kind of new probabilistic way where we're going to try to calculate these abstract wave functions. And then from these wave functions, we're going to try to calculate measurable values. But the catch is, I can't calculate exactly what a particle's position is going to be. I can't calculate exactly what its momentum is. All I can do is tell you the probability of finding the particle at a certain position, the probability of finding the particle with a certain momentum. And so I want to give you kind of what I think is a good way of thinking about quantum mechanics and what we're calculating. So, in general, we cannot say with any certainty where a particle is located in quantum mechanics until we do a measurement. Okay, so even though I can't calculate exactly where a particle will be, once I do a measurement, I can locate it exactly. Okay, so that's a distinction. So at best, we can calculate the probability of finding the particle within a region of space. So just to go further, we likewise can't predict what velocity or momentum a particle will have. I'm sure you talked about the Heisenberg uncertainty principle. So in fact, the better we will review it ourselves, the better we know a particle's position, the less we know about its momentum, the more spread the distribution of momentum would be. Okay, so momentum a particle will have. Okay, so here's the part that I really wanted to get to. So a useful mental picture to have in mind. So what we're going to do is we're going to imagine that we prepare an ensemble of systems. And so that means, like, let's suppose that our system is an electron in a box. What we're going to do is we're going to prepare like Avogadro's number of identical systems. So it's the same size box with the same identical electron, but it's just copies of that electron. And that box has the same set of initial conditions. Its temperature is the same, and all the characteristics that you could think about, all the electric and magnetic fields inside that box are identical. So it's not the exact same system, it's copies of the system over and over and over again. And what we could do is we could say, okay, I'm going to take the first system of this ensemble and I set my system up so it has the exact initial conditions at t=0. I let the system evolve for a time t naught. And then when t is equal to t naught, I measure where is that particle inside the first box. And then I do the exact same thing with the second box. I take it, I give it the exact same initial conditions. I let the system evolve for a time t naught. And at t naught, I measure where is that particle in that box. It'll be different answer that I got from the first one. And I do this for all Avogadro's numbers of these systems. And then I make a histogram of all the positions I found. And that histogram is the probability distribution for the position of that particle. And when we calculate our wave functions and square it and plot that probability distribution, that's the exact same thing. Okay, so you should think of our calculation of wave functions and then squaring it to plot out that probability density is exactly analogous to measuring identical systems one by one and collecting a histogram of all those results. Okay, so I'm going to try to write that down. It will probably not sound great, but anyways, that's what I'm going to attempt to do. So we imagine preparing an ensemble or many identical copies of a system, like an electron in some potential v of x, or if you like, that potential could just be a box with hard walls or something like that. So now we measure the position of the electron at some time t naught in each system inside the ensemble, one by one. And then we construct a histogram of the results. Okay, and so what that histogram might look like is the following. So first of all, before I draw the histogram for our quantum system, if we did this in classical mechanics, like I took a marble and I put it inside, like on some hill that represents my potential. And I start the marble at the same spot in all my copies of the system. I let it go, and then I measure where it is in T naught. Every single system in that ensemble, I'll get the exact same answer. So my histogram classically would just be like this, just a sharp spike. We always get the particle in the exact same position. That's not what happens in quantum mechanics. Instead, we get some distribution that can look like whatever we want. Maybe there's a gap here somehow, and there's some peak. And if we had this for like millions and billions and Avogadro's numbers of systems, this discrete histogram would approach a smooth distribution. And that smooth distribution might look something like the following. And so this smooth distribution in the limit of an infinite number of ensemble copies of the system is just telling us the absolute square of the wave function. So that's the mental picture you should have in mind. In fact, this idea of ensembles is very, very important, not only in quantum mechanics, but when you take statistical mechanics. Our version of that course is 403. So you use the same kind of thinking in that course. Okay, so in the limit of infinite identical systems, the histogram becomes a smooth, continuous distribution that reveals the position dependence of the square of the wave function. All right. So I want to just contrast this with what would happen is if I did this process not for a large number of copies of the system, but what if I just took one system and measured it over and over and over again? Okay, so there's a distinction between what you would see. So if you did measure the exact same system repeatedly, you'd find the following. Okay, so if so if the second measurement was repeated immediately after the first, so here's the scenario. You set up this one box, you put the one particle in it, you set up whatever initial conditions you like, you wait at time t naught, you make your measurement, and your particle's at some position. And then a very short time later, you make another measurement of its position. You're going to find that it's basically the same results, right? You're not magically going to see the particle jump to a new position like an infinitesimal time later. Okay, you would get the same result, say, for the position of the particle. Now, it may seem obvious that you would get the same position. After all, if I measure the particle's position and then like a femtosecond later, I measure it again, I shouldn't expect it to have moved very far. But if you think about it, that means that something drastic has changed about the system's, the particle's wave function. Because we said all we can do is calculate a probability distribution for where we're going to find the particle. But now we have a situation where we've made a sequence of two measurements spaced closely in time that we know are going to give the same result for the position. I don't know what I'm going to get for the first measurement. I only know the probability distribution, but I know the second measurement is going to be the same as the first. So it must be that after we make that first measurement, the wave function of the particle has changed dramatically. It's changed dramatically so that all of the area under the wave function is right at that position of that we found after the first measurement. So it must be the case that making the first measurement dramatically alters the wave function of the particle. And so let me try to represent that as a picture. So we would have, say, as a function of x, here's the absolute square of the wave function. And so maybe this is just before the first measurement at t naught. So maybe we could say t is equal to t naught minus epsilon, where epsilon is some tiny number. Okay, so epsilon is much, much smaller than t naught. Okay, so just before that first measurement, we could have any like arbitrary probability distribution here, right? I'll just draw it like that. Okay, so I don't know where the particle is going to be. It's going to be somewhere in here. I'm most likely to find it here, but that doesn't mean that is where I will find it. Okay, and then we go and we say, well, what about just after this measurement? So here's x, and here's the square of the wave function. And now we're at time t is equal to t plus epsilon, t naught plus epsilon. So this is just after the first measurement. Okay, let's suppose that when we did the first measurement, we actually found the electron was sitting right there. Okay, and so maybe this is x1, the result of the first measurement. Well, what's going to happen is if I make a second measurement right after that, I know I'm going to get the same result. And so it must be that my probability is concentrated right around x1. And so the act of making the measurement has dramatically changed the wave function. So it looks like this. It's sharply peaked right around x1. Maybe in whatever that time epsilon is, the particle could have moved slightly away from x1, so our distribution has some small width, but it sharply peaked right at x1. Okay, and so this is assuming the first measurement at t naught resulted in x equals, I guess I should have, it would be better to say x naught here. So let's do that. All right. So if we said instead, well, what if we made one measurement on our system and then we waited a long time? So we waited not a time epsilon, but a time delta t, where delta t is large. Well, then right after the measurement, our wave function would be sharply peaked like this. But after that, the wave function will evolve, and its evolution will be governed by the Schrodinger equation. The time evolution would be governed by this. So it's going to be determined by some potential and some derivatives of this wave function. And so after a long time, it'll evolve and the probability distribution will spread out and will again be stuck by only being able to calculate probabilities of finding the particle somewhere. So if we did a third measurement on the same system at t equals t naught plus delta t, where delta t is very large compared to t naught, then the wave function, so WF I'm going to use for wave function. So this is wave function, evolves according to, according to Schrodinger's equation, equation number 1. And we once again have a spread, or I don't know, a probability distribution that is spread over time until that new measurement is made, right? So once I make that third measurement, I'll get some value, some new value of x, not x naught, some new value x prime, and that wave function will be peaked around x prime, and then it'll evolve again according to Schrodinger's equation. So just to complete this picture, we would have something like x and the square of the wave function. This is now at time t equals t naught plus delta t, say minus epsilon. So this is just before the third measurement, but a long time after the second. Okay, and so there's going to be some new probability distribution. I don't know what it's going to look like. It'll depend on the details of the potential. Okay, but so maybe it's something like that. Okay, good. So we have 3 minutes left, and I think I can write down. Oh, yeah. Good. So that's perfect. So in the language of quantum mechanics, the first measurement collapses the wave function such that it is sharply peaked near x naught, the position of the particle bound by the measurement at time t naught. So that's the language that's used, this collapse of the wave function. Collapses. I'm not sure that that's exactly the best kind of language, because if you look at this picture, you know, collapse, I kind of think if I said a building collapsed, I'd have a tall building and then it would just turn to rubble on the ground. But that's not what's happening here. It's a collapse in the x coordinate, okay? So we were spread out in x and then it collapsed along this x. It didn't collapse vertically, it collapsed along that x dimension. But I mean, it may not look like it from the way I've drawn things, but it would be the case that this area under here would have to have area 1. And the area here would also have to be area 1. And the area over here, after we let it evolve again after collapse, is also going to have area 1. Okay, good. So I think that's where we'll stop for today. What we're going to do, I don't know when we meet. Do we meet Wednesday, Monday? Okay, so what we'll do on Monday is we'll look at some examples of these sorts of effects. It'll be like a double slit experiment with electrons, which you probably already have looked at, probably in Physics 200. Then we'll do a little review of the, like a slight little motivation of the Heisenberg uncertainty principle. Again, it'll be sort of at the Physics 200 type level. But after that, we'll start to get into review some of the basic statistics that we're going to use to calculate expectation values and things like that. And then we'll be into new material. All right, that's it. Thank you very much. And we will see you on Monday. Yeah.
Very